All right, so this is a short video that just talks about periodic table trends. However, let's start with a little bit of review about the periodic table, shall we? So in your handout, you've got this, how do electron shells relate to the periodic table? Now remember what an electron shell is. It is an energy level, right? Those are synonymous terms. I could call it a shell, an electron shell, or an energy level. And we're talking about the same thing. And how they relate to the periodic table is they are represented by the rows. All right, so rows is another word that I'll put here. So everything that is on the first energy level number 1, is hydrogen and helium, right? With a total of 2 electrons. And as we already learned, those are in an S block, right? The periodic table's one big fault is the way it treats hydrogen and helium. There was just no good way to accommodate that. So even though they're both in the S block, helium's over here because it's a noble gas. Hydrogen is actually a nonmetal, right? We can see that from our descriptions down here. And yet he had to go somewhere. The most logical place was here in terms of electron placement. So there he is there, but he's colored pink to show his status as a nonmetal. It's all pretty strange, isn't it? So energy levels are represented by the rows of the table. So if I talk about the third energy level, I'm talking 1, 2, 3, about this energy level that starts off with sodium and goes all the way through argon. All right, if I'm talking about the sixth, 1, 2, 3, 4, 5, 6, cesium all the way across to whatever Rn is. It's written very small and I can't read it. Radon probably, or something like that. All right, so we know that that's the case now. So what about the columns? What do the columns represent? The columns represent the number of electrons that are in that particular column as valence electrons. So remember, a valence electron is the electrons that are in the outermost shell in that atom's configuration. And generally the valence electrons, that shell is not completely full. We regard it as full when it has 8 electrons, like all the noble gases do. At that point, they are not reactive because that shell is full. They're not interested in getting rid of any electrons or gaining any electrons. And so they become extremely non-reactive. But over here, everything to the left of the noble gases has incomplete valences. And so they are looking to engage with certain other atoms in order to fill their valence electrons. So what we know is that in column number 1, all of these particular elements only have 1 valence electron. That little valence electron is flying out at a huge diameter away from the central atom. And because of that, it can easily be picked off. Whenever this column of atoms, this group, we call it family, and it's group 1A is the way we'll refer to it, they always will ionize to a +1 charge. And think about what +1 as a charge means. It means that it has lost that 1 electron that was flying out lonely in its own little valence, right? So because the electron is negatively charged, losing it creates a positive charge. Our next column we call 2A, and this column always ionizes to a +2 charge because it's got 2 lonely little valence electrons that again can be fairly easily picked off and so result in a +2 charge on that particular atom. All right, over here is column 3A, and you guessed it. If you think about it, this is 1s2, 2s2, 2p6, right? So we've got a total of 1, 2, 3 valence electrons here in boron, aluminum, gallium. All right, we have 4 electrons here, 5 here, 6 here, 7 here, and then here we've got 8. So this is full, right? A full valence. Now think about this. These guys in this 7th column, they only need one more electron in order to be a full valence and be super happy, right? So they are desperately looking to find one more little electron that they can pick off, get away from somebody typically over here, to make their 8 valence electrons. So we'll learn a lot more about that in the next chapter, but just know for now, this has 7 valence electrons, and because of that, when it ionizes, it likes to gain 1 electron, and so in this column, we ionize to a -1 charge. And you guessed it, with 6 valence electrons, they're trying to gain 2 electrons to fill out their valence, right? And so when they ionize to a -2 charge. So you can say categorically that everything in this group, family, or column, right, it all means the same thing, is going to be ionizing to a -2 charge. Okay? Over here, do you think these ionize to a -3? Yes, they do. Now, coming from this direction, if we had a +1 and +2 here, right? This guy here, if you guess that he ionizes to a +3, you would be correct. What about carbon and silicon and all those? They're a little bit more complex. Yes, they can ionize, but what in general you need to know is no ionization happens here. They keep all their own electrons in the noble gases. But here, where I'm trying to get one, I ionize to a -1. This column to a -2, this column to a -3. And accordingly, when I've got one that can be easily picked off and removed, I ionize to a +1 in this column and a +2 in this column. Now, what you can deduce from what I've told you about these then is that when you think about chemical reactions and chemical properties, everybody who is in the same column has the same chemical properties, right? So if I were to ask you what element is most similar in its chemical properties to sodium, you're going to pick lithium, potassium, rubidium, cesium, francium, somebody like that. That's there in that column, that's in the same family. If I ask you who has the same characteristics as aluminum, you're going to go down here in the green and say these guys would, right? Chlorine, you're going to go here, right? So know that families are grouped this way in this particular order to arrange them by their chemical similarities and how they behave in chemical reactions. Okay, so we've seen that the periodic table is very much set up by its electrons, right? Sure, the protons march across here and add 1 proton as we go through each element here. We can see that through the increasing by 1 atomic numbers of everything. But know that the way we set up our columns is strictly due to the electrons. And so what we see is, if you think about it, this column represents the S block, all right? And that makes sense, right? We know that an S can have a maximum of 2 electrons in it. Over here, we've got the P block, all right? Now, in S, I should say, here's our exception. This guy goes over here, right? Because this forms 1s2 when full. All right, so here's our P block, right? And that makes sense. We said S could have a maximum of 2, P can have a maximum of 6, 1, 2, 3, 4, 5, 6, right? We got it. Come down here, this guy is the D block, all right? And we said D could have a maximum of 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, and then what do you think this is? You're right, this is the F block, right? And if you counted it up, you'd find going across it actually has 15. And you'd say, well, wait a minute, what on earth is going on? But it's got the 14 that we expect, that we think of as having an F, but there's one more here that's interacting with the D block, right, to fill out the D block. So this is sort of a strange little thing, All you need to know about this is here's my S, here's my D, here's my P, here's my F, right? And you need to know S has a maximum of 2, P has a maximum of 6, D has a maximum of 10, F can have a maximum of 14. All right, now we had to back up and do that. All right, I've already covered this. What do you know? Okay, but let's go down then to similar characteristics. We've already talked about that pretty much, about the columns and then the colors. Both have great meaning. So if you're asked about the similar characteristics, you're going to look within the group and within the column to find the ones that are the most similar. All right, so let's get into periodic trends. The biggest one to know, actually, I'm going to skip down to the bottom page here of your handout, and that is electronegativity. We'll be talking about this throughout the entire year. So what is electronegativity? It is the ability to attract electrons. Attract electrons. All right, so if you think about who wants to attract electrons, it's somebody whose valence shell is almost completely full, right? So the prime suspects are right here. Additionally, it's going to be somebody who has very little electrons between it and its nucleus. And therefore, fluorine is our absolute #1 candidate. It is the most electronegative element that is out there. Think of fluorine as that little girl on the playground who's trying to grab the ball away from everybody else. She's kicking and punching to get that ball. She is the most aggressive thing out there. That is fluorine. Go down here. The least electronegative is francium. All right, francium is the, yeah, whatever, dude. You want electron here? Go, here it is, right? He doesn't care. Why is that? He's got tons of energy levels, or electron shells, between him and his nucleus. And because of that, that proton in the nucleus can have very little hold to hold that outer valence electron, that one little lonely electron, right, because it's in the first column, towards it. And therefore, francium gives up electrons extremely easily. Everybody else gives them up pretty much relative to how close they are to fluorine. So if I ask you which is more electronegative, this guy or this guy, it's clearly going to be this guy, right? He's closer to fluorine. If I ask who's the least electronegative, this guy or this guy, you know this guy is. He's furthest away from fluorine. All right, so that's electronegativity. Now let's talk about ionization energy. So ionization energy is the amount of energy it takes to remove one electron. All right, so ionization energy, I'm removing one electron. We're going to ignore the noble gases for right now. And again, this makes sense. Fluorine was the big pig who wanted to grab everybody else's. So of course, she also wants to keep all of her own and will fight to do so. Okay, again, francium, he doesn't care. Sure, you can have it, just take it, right? So it makes sense that both ionization energy and electronegativity, which are sort of opposite functions from each other, would have the same least to most, right? Okay, now let's go on and let's do atomic radius. Now, atomic radius is another chemistry is evil moment for us. On one hand, it makes sense that the radius is the smallest with little hydrogen, right? He's only got one proton and one electron shell, and that electron shell only has one little electron in it, right? And even with helium, that's just a max of 2 electrons. So it makes sense that that's a very tiny atom, and that as you go down the periodic table, our atoms get bigger and bigger and bigger, right? And remember that when I talk about atomic radius, I'm not talking about the radius of only the nucleus. I'm talking about the nucleus and then all of the electron shells that are around it. Okay, so this makes a lot of sense, doesn't it? What doesn't make any sense at all when you first look at it is why, if I'm adding protons as we go across, I can tell that by the atomic number, right? And I know that since these are neutral elements, when I add a proton with its positive charge, I'm adding an electron with its negative charge, right? And so I'm getting bigger and bigger in terms of mass here, right? But what I'm saying to you is, yes, bromine atom is far bigger in mass than a potassium atom. That's true. But the potassium atom actually has a bigger atomic radius than everything that follows it along this row. Now, how could that be bigger? It's because when you get to that outermost energy shell, that valence electron shell, if I only have one little electron, he is super far away from everybody. Okay, he's really hanging out there dramatically far away, and he's easy to get picked off. Okay, so because of that, as I add more and more valence electrons, which I do as I move to the right across the periodic table, those greater number of electrons are actually pulling in more toward the protons in the nucleus. All right, so as you go across here, we're pulling in more and more and more, and so we're getting smaller as we go across this way. Okay, all right. Again, super illogical, really think about it. Metallic character. Now, when you think of a metal, you probably are thinking of things like iron and tin and gold and silver, right? Let's see, what else might you be thinking of? Manganese, right? Zinc, things like that come to mind for you. You don't so much think of these guys as having a metallic character, but they do. Even though we don't see them in our everyday world so much, because they're highly reactive, so they're pretty almost always in compounds, but they are considered the most metallic of all, because the way that we're defining metallic character is by its ability to ionize to a plus charge. All right? So that's all it is. And it makes sense that here, where I'm really likely to lose these electrons, right, that I'm enhancing my ability to ionize to a plus charge. Okay. And then finally, we'll talk just a second about proton pull. Proton pull says, what effect can the protons with their positive charge have on the electrons that are circling around them? And here what I see is when I have very, very few energy levels, my ability for that proton to interact with the electron increases dramatically. Okay, so as we go upwards here, we're getting more and more of an effect with the protons keeping their electrons close by. As we move across the table, what we see is there are more and more protons, right? I'm adding one for every box as I move rightwards, and because of that, my pull is increasing as I go across. Okay, so know that. And then finally, the electron shielding effect. And again, think of this as the opposite of a proton pull effect, because it's working in the reverse way. And what that's saying is, well, it's like if you go to a concert, right? And there's your favorite performer. When you're on the front row, right near it, you can see everything, and it's really great, and it's an intense experience. If you're in the stadium, an arena, and you're in the very back row, you can't really see that performer anymore, and he's not going to have the same effect on you. So same thing here. I've got my positively charged protons, and the more electron levels, energy levels, shells that are between me as an electron and the proton in the nucleus, I'm going to get more and more shielding, and that proton's going to have less effect. So it makes sense that these are sort of the reverse of each other as well. All right, let's see. I think that's all we need to do.